In this video, we're going to go through example 10.4. This is one of the in-chapter examples from the textbook, Shigley's Mechanical Design, 9th edition. Here we're approaching the analysis of a helical compression spring. We were told a number of things about this spring, and then we're asked to evaluate safety factors as well as its critical frequency. In this case, this is not a design problem, but rather an analysis problem, because we are given the design and it's up to us to evaluate the design. Let's go through the different items that are provided to us. So we are assuming here that this is a constant diameter helical compression spring, that it's made out of music wire, and that it is what we call as wound. So what does it mean if we have an as wound spring? In this case, we're referring to the manufacturing process. When we form the spring, we will often have residual stresses that arise from that. And one of the options that we have in manufacturing a spring is to go through a thermal treatment to release residual stresses. But if we specify as wound, then that means that we don't use the thermal treatment. If instead we say this is a set removed spring, that's where we go through the thermal treatment. So this is made from music wire and is as wound. We're told that the wire diameter is 0.092 inches, so just under 1/10 of an inch. We're told the outside coil diameter is 9/16 of an inch. Now, this is different from the helix diameter. We're going to need the helix diameter in some of the later calculations. The outside coil diameter, that's going to be equal to the wire diameter plus the helix diameter. So that is going to be equal to 9/16 of an inch. And then with that equation, we can solve for what is the helix diameter. We're told that the free length is 4 3/8 of an inch, that the number of active coils is 21, that we have squared and ground ends. So with these boundary conditions, this affects a number of things, and it basically provides a nice flat surface at the ends of the spring for the components that are in contact with it. We're also told that this is unpeened. So what does this mean? You might recall that in specifying a spring design, we can choose to go through an additional process called peening, where basically we impact the outer surface of the spring using some very small particles. And the impact of these small particles introduce compressive stresses, and these compressive stresses then bias the stress in the spring toward compression and away from tension, and this can help us with fatigue. If you think back to our coverage of fatigue, if we have tension, that's going to help accelerate crack propagation. And so peening is something that can help with fatigue. And so when we go through our fatigue calculations in this example, we're going to see what impact that has. Now, in the textbook, the exposition of this example is rather succinct. And so in this video, I hope to go through some additional detail that might be helpful in understanding this and other similar examples. We are asked to obtain 4 different quantities: the fatigue design factor using the torsional Gerber failure criterion for fatigue using Zimmerli data, and then part B, find the fatigue safety factor using the Sines failure criterion using Zimmerli data. And Sines is a failure criterion that is new in this chapter. We will talk about that a little bit more. It is specific for torsion. And then part C, find the fatigue safety factor with respect to the torsional Goodman failure criterion. And then finally, let's find out the critical frequency. There is some information here that is missing. We can certainly calculate the critical frequency, but we cannot perform an evaluation of whether this critical frequency is high enough or not, because we're not told much about the application. We don't know what is the frequency of the loading applied to the spring. We're actually not told either the number of cycles to expect. And because we are applying these fatigue failure criteria, that this is not just static service, but we do need to design for fatigue. Let's go through a number of initial calculations that will be common to the first three parts of this problem. And then we'll go through and step through the process to work out how do we actually calculate the safety factor based on each of these failure criteria. The process is going to be failure criterion specific for parts A through C. So there's some interesting differences there. And then after that, we will go through the critical frequency calculation and have a little bit of discussion there. And also along the way, we'll try to see if we can extract any design insights from this analysis procedure. Let's go through the initial common calculations. First of all, we need to know what is the helix diameter. That's going to be equal to 9/16 of an inch minus the wire diameter, or in other words, 0.5625 inches minus 0.092 inches, or 0.4705 inches. So you will see this number used throughout the calculations. The next thing we need is the spring index, and this is going to be used in a few different places. And in addition to being an input to other calculations, this is something we should check anyway to see if it is within the desired range of spring index values. So the spring index we can calculate as the helix diameter divided by the wire diameter, which then is 0.4705 divided by 0.092. And we find out that this helix diameter is 5.11. It is unitless. We have a length value divided by a length value. And this helix diameter, the spring index needs to be between the values of 4 and 12. You might remember that if we are on the low side, if we have a spring index of 4, then that means, or lower, then we have a really small helix diameter relative to the wire diameter. And this is going to be hard for manufacturing. This has a higher propensity for introducing surface cracks, and that also is problematic for fatigue. But if we are on the high side of the spring index, then we're going to have a very large helix diameter relative to the wire diameter. And this constraint has more to do with packaging and handling. So we, at the high end of spring index values, would have springs that are sort of like slinkies, and they can very easily get tangled up with each other. Another thing that we're going to need is a stress concentration factor. And the Bergstrasser factor, it accounts for the helix curvature. And it's equal to 4 times the spring index plus 2 divided by 4 times the spring index minus 3. And if we plug in this 5.11, then we get 1.287. That's going to come into play, of course, in stress calculations and in fatigue calculations. Let's review how we calculate shear stress in a helical compression spring. In general, this is going to depend on both the torsion introduced in the spring wire due to the moment arm, that is the distance between the wire center and the axis of compression, and this is what results in the twisting of the spring wire. And then we also have the shear. And the combination of shear and this torsion produces shear stress, and the maximum shear stress is going to occur on the outer surface of the wire. And after algebraic manipulation, the maximum shear stress is going to be equal to this stress concentration factor times 8 times the axial compression force times the helix diameter divided by pi times the wire diameter cubed. And as we've talked about before, this wire diameter has a very nonlinear relationship with stress, and therefore is something really to pay attention to. If we have issues with meeting stress constraints, this 1 over diameter cubed factor is going to have a big impact on stress. What stresses are we going to need to obtain these fatigue safety factors? If we don't have completely reversed stress, we're going to need both the stress amplitude and the mid-range shear stress to find the various fatigue design safety factors with respect to the 3 different failure criterion that we're considering here. In addition to obtaining these 2 different stress quantities, we're going to need the strength amplitude and the mid-range strength amplitude. And this is from Zimmerli data that we've discussed before. It's a really interesting result that applies specifically to spring fatigue analysis. We also are going to need the ultimate tensile strength in shear, and we're going to use results from the chapter on springs to estimate that. And remember, that depends on geometry as well, not just material. So how are we going to get these stress quantities? We're going to need to know, well, what is the alternating force and what is the mid-range force? Let's think about the fluctuating stresses here. Suppose the horizontal axis is time and the vertical axis is force. In this problem, we are given 2 different things. We're told that the preload is 5 pounds and the maximum load is 35 pounds. So what is the preload? If we have a spring installed in an application and there's no other external force applied, this is a level of force that always exists. And so this is the minimum force. We are preloading the spring with 5 pounds. And then the maximum load is 35 pounds. So we have these maximum and minimum values, but something you might have noticed from the textbook is we were not really told anything about the nature of the variance between 5 and 35 pounds. Only that fatigue is important. We don't know if this is harmonic or some other type of variation with time, but this actually doesn't matter. The shape doesn't really impact fatigue. It's really just the number of cycles that impacts fatigue. So we can have some arbitrary shape, and we just need to know what is the maximum force and what is the minimum force. Then we can calculate what is the alternating force and what is the mid-range force. So the alternating force, that is going to be equal to the magnitude of the maximum force minus the minimum force divided by 2. And the mid-range, that's going to be equal to the maximum force plus the minimum force divided by 2. Now, this formula is the average or the mean between the max and the minimum force, but if we think about a general force trajectory here, it's not necessarily going to be the mean or the average of this trajectory. It could be biased to one side or the other, but in any case, when we are using the models that we cover in class for alternating stresses, fluctuating stresses, and their impact on fatigue behavior, the important thing here is the mid-range stress and that's defined here as the maximum stress plus the minimum stress or force divided by 2. Here we're looking at force first, and then we're going to apply this shear stress equation to find out what is the maximum stress and the minimum stress, and then we can calculate what the alternating stress and the mid-range stresses are. Once we have these, along with the results from Zimmerli data and the shear ultimate tensile strength, then we can go through a process to calculate the fatigue safety factors, and it's going to be different for each of these 3 failure criterion. And then finally, we'll go through the calculations for critical frequency. What is the mid-range force? 35 pounds plus 5 pounds divided by 2 is 20 pounds. What is alternating force? 35 pounds minus 5 pounds, the magnitude of that divided by 2 is 15 pounds. One thing to note here is that while this force is always applied in compression, it is not necessarily all compression in the material. Think about the mechanics of a helical compression spring. We are going to have a combination of shear and also of torsion. And so we are accounting separately for both the mid-range force and the alternating force here. How are we going to get the alternating stress? We're going to take the shear stress, maximum shear stress formula that we calculated before, and insert the alternating force. That's going to be equal to the shear stress concentration factor that accounts for the curvature of the helix, 1.287, times 8 times the alternating force of 15 pounds times the helix diameter of 0.4705 inches divided by pi times the wire diameter, 0.092 inches cubed. And we need to pay attention to units here, making sure that we are consistent across the board. If we want to put this in terms of kilo-psi or ksi, then we multiply by 10 to the minus third, and this is going to be equal to 29.7 ksi. That's a quantity that we're going to use repeatedly in the following calculations. And then to get the mid-range stress, we simply use the same formula, but instead insert the mid-range force. Remember, the mid-range force is 20, and so we keep everything the same, but we replace the force with 20 pounds, and that's going to be equal to 39.6 ksi. And something that you might notice is the ratio between these, the alternating and the mid-range stress. That's going to be equal to 0.75, and that's something that we're going to use later in our calculations, and we can also identify that same ratio using the mid-range force and the alternating force. Let's think about where we're at and where we need to go. The quantities that we have right now are the alternating stress and the mid-range stress. We're after the fatigue safety factors. So how do we get those? What do we need next? We need the ultimate shear strength. We also need the alternating shear strength or the mid-range shear strength, one or the other. And we need the shear endurance limit. The shear endurance limit is going to depend on the failure criterion. These quantities, these relate to the intersection of the load line that we discussed at length in previous sections on fatigue with the curve defined by our fatigue failure criterion. And we'll go through this in a bit more detail to make it very clear when we get to that point. Right now, let's focus on calculating the ultimate shear strength. If we go to equation 1014, we get this model for the ultimate tensile strength, not the shear strength yet. And that's going to be equal to a quantity A divided by the wire diameter to the power of m. A and m are numbers that we need to look up in a table that depend on a few different things. If we go to table 10.4 in the textbook, it depends on material and also size. Remember, we're using music wire in this application, and if we have a diameter in inches between 4/1000ths of an inch and 0.256 inches, that information combines to produce a value of A, this coefficient, of 201, and that is in units of KSI times inches to the power of m, and m is this exponent that we are obtaining from the table, and m is equal to 0.145. And this wire diameter that we're using here, d is equal to 0.092 inches. That is within this range, and so we can be confident in using these quantities in estimating what the ultimate tensile strength is. So plugging these numbers in, the ultimate tensile strength is going to be equal to 201 divided by 0.092 to the power of 0.145. That's going to result in 284.1 KSI. And then we're going to need to determine the ultimate shear strength. And using one model for this estimation, that's going to be equal to 67% of the ultimate tensile strength, or 190.3 KSI. We're going to see this quantity, 190.3 KSI, show up in quite a number of our calculations as we move forward. One quick note, just thinking about the information that is in table 10.4, another thing that's provided in that table is relative cost. This cost is relative to hard drawn carbon steel wire, where its relative cost is 1.0. The relative cost of music wire is 2.6, so it's a moderate cost material to be making a spring out of. There are other materials that are quite a bit more expensive. For example, some stainless alloys that are used for helical compression springs have a relative cost of up to 11. And in applications where the environment demands something like stainless steel, then this might warrant the additional cost. Let's now think back and reflect on what items we know and what things we have yet to determine. Known quantities include the alternating stress, the mid-range stress, and now the ultimate shear strength. We still need a number of other items. We need to know the Zimmerli data for the alternating shear strength and the mid-range shear strength. And we're going to need to know a few other quantities. But if we go to equation 1028 and note that the material we are using is unpeened, then we can just directly obtain the quantities for the Zimmerli data. And so here we're going to be using 35 KSI and then 55 KSI for the mid-range shear strength. Now, this is not the actual strength of the material. Remember, with the Zimmerli data, it is specified with the goal of obtaining an estimate for the shear endurance limit. We are going to calculate other values for the projection of a point in the alternating and mid-range stresses that will also use the same symbols, the alternating and the mid-range shear strengths. And we're going to be using these quantities to calculate what is the fatigue safety factor. So it's a little bit of a challenge to keep all of these straight. When we are talking about Zimmerli data, these quantities are purely for the purpose of calculating the endurance limit. To make this a little bit more clear, let's think about this space where on the horizontal axis we have the mid-range stress. On the vertical axis we have the alternating stress. And suppose we have a point that describes our stress state for a given spring. So here we have the mid-range stress, which we've already calculated. Here we have the alternating stress, which we've calculated. And the ratio of those gives us the slope of this line, this load line. R is the quantity that we use to describe the slope of that line. And depending on the failure criterion that we use, this load line is going to intersect the failure criterion curve at a different place. So if we are using, for example, the Gerber failure criterion, it's going to intersect the vertical axis at this location of the shear endurance limit, and then it's going to intersect the horizontal axis at the location of the ultimate shear strength. And this is a quadratic formula, so it's not going to be a straight line. It's going to be a curve. If this is an approximation of the Gerber failure criterion. And this point of intersection is important. I'm going to call that point A. I'm going to call the origin O, and then I'm going to call this point that describes the actual fluctuating stress of our component as point B. If we want to characterize the safety factor with respect to fatigue and a particular failure criterion, we need to compare the distance from the origin to B and the distance from the origin up to A. So there are a few different ways we could do that. If we are projecting A onto the vertical axis, then this is what we will label as the alternating shear strength. If we look at the projection onto the horizontal axis, that's what we're going to label as the mid-range shear strength. And if we obtain either one of those, then that's going to help us obtain the ratio of this distance from O to B to the distance from O to A. And that's going to give us our safety factor. We want to make sure that as we travel along this load line, we don't cross over this intersection point A. And also keep in mind that when we are considering these different failure curves, such as the Gerber curve here, these are really to be thought of as fuzzy boundaries. As we approach or cross this curve, it increases the probability of a fatigue failure. It's not a black and white sort of constraint where as long as we're below it, we're safe, or if we go beyond it, we're not safe. So it's important to think in terms of the probabilistic nature of these failure criteria. The next step, the next question, is for a given failure criterion, such as Gerber, how can we find the shear endurance limit? This is something we don't know ahead of time. And the whole point of obtaining the Zimmerli data here is to determine the shear endurance limit. So how do we obtain that? Let's use Gerber as an example, and let's assume that the fatigue safety factor is equal to 1, and then that's going to put us right at point A. And we find out that is the alternating shear strength from Zimmerli data, at least in this application, divided by the shear endurance limit, plus the mid-range shear strength from Zimmerli data in this application, divided by the ultimate shear strength, that quantity squared, all equal to 1. Now, if we know these quantities, then we can solve for the endurance limit for shear. So that's going to be equal to the alternating shear strength divided by 1 minus the mid-range shear strength divided by the ultimate shear strength squared. Now here we are plugging in the quantities from Zimmerli data, and that's going to be equal to 35 divided by 1 minus a quantity, 55, divided by the ultimate shear strength that we calculated earlier, and that is 190.3. Remember that depended on both the material and on the wire diameter. And then this quantity is squared, and that turns out to be 38.2 KSI. Again, remember this quantity, this is not the intersection here in this space, but rather this comes from the Zimmerli data. These are two distinct things, and it can get a little bit confusing because the same symbols are used in the textbook to mean two different things. How do we get the safety factor? I mentioned that it's the ratio between these distances, OA and OB. Let's zoom in on this triangle. Suppose that's O, that's A, this is B, and then this height right here, that is the alternating shear stress. And then this height right here, this is the alternating shear strength. And we want to know, well, what's the ratio between these two different distances, OB and OA, and that's going to give us the safety factor. More specifically, the fatigue safety factor is going to be equal to the line OA divided by the line length OB. But looking at these triangles, these are similar triangles, and it's possible to show then that this ratio is going to be equal to the alternating shear strength divided by the actual alternating shear stress for our given stress, fluctuating stress state at point B. So that is what we're after. We want to know what is the fatigue safety factor. And just conceptually, as we're moving around in this space at A, the fatigue safety factor is equal to 1. As we move closer to the origin, as we reduce either the mid-range or the alternating shear stress, and we move along this load line, then we're going to have a fatigue safety factor that gets bigger. It's going to be greater than 1, strictly greater than 1 as we move closer to the origin. So how do we calculate this? Well, so we could either obtain the alternating shear strength and compare it to the alternating shear stress, or we could obtain the mid-range shear strength and compare it to the mid-range shear stress. In the textbook, the way these formulas are used, looking back at the chapter on fatigue, it turns out that the authors solve for the alternating shear strength first, and then solve for the mid-range shear strength. We only really need one of them to get the safety factor, but once you have one of them, you can easily calculate the other. Let's have a look at how we can obtain an estimate for the alternating shear strength. We're going to go back to table 6-7, and based on the relationships in this mid-range and alternating stress space, we can solve for the alternating shear strength. And the formula for this based on Gerber is provided in table 6-7. That's going to be equal to the load line slope squared times the ultimate shear strength squared divided by 2 times the shear endurance limit multiplied by -1 plus the square root of 1 plus 2 times the shear endurance limit divided by R times the ultimate shear strength quantity squared. All of these quantities are known. Remember that the slope of the load line was equal to 0.75. And once we plug these in, we get 0.75 squared times 190.3 squared. Also, of course, be sure to keep in mind the units. Here we want to be consistent. If we want the alternating shear strength to be in units of KSI, then we keep all of the other stress quantities in units of KSI. This then is divided by 2 times 38.2 KSI times the quantity -1 plus the square root of 1 plus the quantity 2 times 38.2 divided by 0.75 times 190.3 KSI, quantity squared, close the bracket, and that turns out to be 35.8 KSI. So this tells us how far along the load line we are relative to the point of intersection. And then with this information, we can calculate what is the fatigue safety factor with respect to the Gerber failure criterion. And this is going to be equal to the alternating shear strength divided by the alternating stress. And this alternating shear strength that we approximated from this formula is used right here, 35.8 KSI divided by 29.7 KSI, and that equals 1.21. So this is the answer to part A, the fatigue safety factor using the Gerber failure criterion is 1.21. Now for parts B and C, we need to calculate the same quantity, the safety factor, but based on 2 other failure criteria. And then finally for part D, we need to determine the critical frequency for the spring based on the wave equation. For parts B and C, we're going to use a very similar procedure. So just to back up a little bit and give an outline of what this procedure actually was, we started with a number of knowns. So we right now know the alternating shear stress, we know the mid-range shear stress, and we know the ultimate shear strength. And these apply to any of the failure criteria. But for parts B and C, we need to find a few things that are specific to the failure criteria. And that includes the endurance, the shear endurance limit, the alternating shear strength, And then also, then we can calculate the fatigue safety factor. Now remember here, I am talking about the projection of point A onto the vertical axis and not about Zimmerli data. So let's go through and apply this process using the signs criterion and see how the safety factor changes. Now, the signs criterion is introduced in this chapter on spring design. It's torsion specific. It is covered very briefly in section 10-9. And the main idea here is that the alternating shear stress is independent, or the maximum alternating shear stress that we can tolerate and still have infinite fatigue life is actually independent of the mid-range stress. So this is quite different from the concepts we covered in the chapter on fatigue, where mid-range stress actually had a big impact on endurance limit. So here, though, with torsion, if torsion is the primary mechanism for stress, there is some evidence to support this this model that we can go ahead and ignore the mid-range shear in calculating what the fatigue safety factor is. And if that's the case, then this fatigue safety factor just gets dramatically simplified. It's simply the alternating shear strength divided by the alternating stress. The mid-range stress term completely drops out, and instead of looking at the projection of point A, this comes from Zimmerli data. We already have that quantity from Zimmerli data, that's 35.8 KSI, and we already have the alternating shear stress, that's 29.7 KSI, and so with signs we get a safety factor of 1.21. This is the answer to part B. In part C, we need to apply the Goodman failure criterion to determine the fatigue safety factor. There are a number of steps that we need to take. The first one is to find the shear endurance limit. And to obtain that, we can go back to the definition of the Goodman failure criterion. And this is the alternating shear stress divided by the shear endurance limit plus the mid-range shear stress divided by the ultimate shear strength being set equal to 1 over the safety factor. And all of these items except for the endurance limit are known. If we solve for the shear endurance limit, we obtain this, the alternating shear strength divided by 1 minus the mid-range shear strength all over the ultimate shear strength. Now, remember, here we are using Zimmerli data explicitly for the purpose of determining the shear endurance limit. So these quantities are based on Zimmerli data. They're not the projection of point A onto the respective axes. If we plug the data in, 35 KSI over 1 minus 55 KSI divided by 190.3 KSI, that is equal to 49.2 KSI. So now we have an updated shear endurance limit. With this, we can go through the same process that we did before and determine what are the projections onto the various axes and calculate what the fatigue safety factor is. If we go back to the table in Chapter 6, Table 6-6. Now, if we're using Goodman, it's table 6.6 instead of table 6.7. We can find out what the intersection formulas are. But first, to conceptualize that, let's have a look at this space where Goodman connects the ultimate shear strength to the shear endurance limit, and it's a linear formula. It's not quadratic like Gerber. And then we're going to have our load line with a slope of r. Then we have point A, and we're wanting to find the projection of point A onto the vertical axis to obtain the alternating shear strength. And once we have that, then we can calculate the fatigue safety factor. From the table in Chapter 6, we can get this formula where the alternating shear strength is equal to the load line slope, r, times the endurance limit in shear, times the ultimate shear strength, divided by r times the ultimate shear strength plus the endurance limit in shear. Now we can plug all the quantities in. 0.75 times 49.2 KSI times 190.3 KSI, all divided by 0.75 times 190.3 KSI plus what we just calculated, 49.2, and that turns out to be 36.6 KSI. And then again, by observing similar triangles, if this is the alternating shear stress and this is the alternating shear strength, and the slope of the hypotenuse here is r, then the fatigue safety factor is equal to the alternating shear strength divided by the alternating shear stress, or 36.6 KSI divided by 29.7 KSI, or 1.23. This is the answer to part C. Now, these results are all pretty close to each other, but they are distinct. And just reflecting back on these, sines, that was the most conservative, where the fatigue safety factor was 1.18. It's telling us that we are closer to failure than the other failure criterion. And then Goodman, this most recent one, this was the least conservative, telling us that we were farther away from failure compared to the other criterion. And again, remember, these are fuzzy estimates. There's a lot of uncertainty involved in when fatigue will actually result in a failure. And this is super important to understand these relationships to develop a good conceptual understanding of how exactly to design various components or components within the system to guard against fatigue failure. But if you are designing something that is safety critical, where it's very important that we have a lot of confidence that it's not going to fail, and if it's important to shy away from very large safety factors, then it's really important to actually do physical testing to obtain empirical data for the specific materials, the specific components and processing that are going to be applied so that you can have more accurate fatigue failure estimates and more confidence in your designs. Let's move on to part D. Here we need to determine the critical frequency for this spring. We don't know the exact application, so we can't really make a determination of whether this critical frequency is acceptable or not. We would need to know more about how this spring is being used, but here we can at least perform this analysis and determine what ranges of frequencies might be appropriate. Let's have a look first at equation 1025. This equation gives us the critical frequency for a spring based on the wave equation, where K is the spring stiffness, G is the gravitational constant, and W is the weight of the spring, so it's in units of force. And to determine this, well, we can just look up what G is if you don't already remember it. We need to calculate what K is, and we need to calculate what W is. So how do we get K? This is something that should be pretty familiar to you by now. K is going to be equal to the wire diameter to the power of 4 times the shear modulus divided by 8 times the helix diameter to the power of 3 times the number of active coils. Now, in parts A through C, we've not used G, and we've not used the number of active coils before. So these are new things that we're using here. And we've not determined what G is yet. And as with other properties for materials used in springs, often there is a dependence on geometry. And that's the case with the shear modulus. If we go to table 10.5 and we look up music wire, we see that it depends on size, what the properties are. And if our diameter is 0.092 inches, that is within this range in the table between 64 thousandths of an inch and an eighth of an inch. And within that range, so this is the third row down the table specifically for music wire, we see that the shear modulus is equal to 11.7 mega psi or MSI. So we have almost all of the quantities we need now. We can go ahead and calculate what the stiffness is here. That's going to be equal to 0.092 inches to the power of 4 times 11.75 times 10 to the 6th. Be careful with the units there. 8 times the wire diameter, 0.4705 cubed, times the number of active coils, or 21. And that's going to be equal to 48.1 pound force per inch. We have the stiffness. We have this spring almost fully characterized now. We were given what the not only the number of active coils, but also the free length. We were not told what the pitch was, but knowing what the free length is and the number of active coils, and knowing the end conditions, we could calculate the pitch if we needed. But in all of the calculations so far, we've not needed the pitch. This is the first time we've needed the number of active coils. Previously, we've primarily relied on the wire diameter and the helix diameter. So those were important factors in the earlier calculations that focused on stress and fatigue. Now we need to calculate weight. How do we do that? Well, weight is going to be equal to the volume, area times length, times the weight density. Just looking at units here, this is going to be in inches cubed. This is going to be in pound force per cubic inch. And after some algebraic manipulation, we get pi squared, wire diameter squared, helix diameter, number of active coils times the specific density, all divided by 4. We have almost all of the quantities here. We don't have the weight density yet. And you might be wondering, well, how do we get that? We can look up in the appendix quantities like this for a range of materials. In Appendix A5, we can look up a very closely related material, carbon steel, and for that, the density is going to be equal to 0.282 pounds per cubic inch. But if we were to look at a more comprehensive reference that provides the density specifically for music wire, we would find that it's something else. It's very close, it's only slightly different. 0.2 0.84 pounds per cubic inch. So we're going to use that one, not that one. And if we go back up here, we can plug everything in. Well, actually, we need to get the weight first. So to get the weight, we have pi squared times that's 0.092 squared times 0.4705 inches times 21 active coils times 0.284 pounds per cubic inch, all divided by 4. And that comes out to be 0.0586 pounds. It's a pretty small spring. It's only roughly 9/16 in diameter. What was it, around 4 inches long, if I remember right, was the free length. So it's not a very large spring. We have the weight. That goes in right there. We have the stiffness. That goes right there. What is G in this unit system? That's going to be 386 inches per second squared. Now we have everything we need to calculate the critical frequency. That's going to be equal to 1/2 times 48.1 pounds per inch, the stiffness, times 386 inches per second squared, the acceleration of gravity, divided by the weight of the spring, 0.0586 pound force. That turns out to be 281 hertz. Okay, so this is the answer to part D, but what does it mean? Maybe let's put this in different terms. 16,860 RPM. So if we're using this spring in conjunction with some type of rotating machinery or equipment, this information might be helpful to us. And also thinking back to what is the allowable maximum operating speed or frequency with respect to critical frequency, we're supposed to keep the maximum operating frequency down to less than 1/15 of the critical frequency. So what is F divided by 15, or in terms of RPM? That's going to be equal to 1,124 RPM. So if we have a spring that is associated with a rotating shaft or other rotating system, then the maximum speed we really should operate that is a little over 1,100 RPM. So maybe this is reasonable, depending on the application, but maybe this is way too low. So for example, if we were using this as a valve spring for a car, the design, this is a little bit small and probably not stiff enough for an automotive valve spring. But suppose just thinking through the speeds that this would need to be operating at. What if we had a red line of 6,000 RPM for an internal combustion engine for a car? So the maximum operating speed of 6,000 RPM. Well, the camshaft, you might remember, at least for a 4-stroke internal combustion engine, operates at 1/2 the speed of the crankshaft. So that's going to be 3,000 RPM. Well, 3,000 RPM, that's quite a bit larger than 1,100 RPM. And so if we were wanting to use this with rotating machinery that was operating as fast as 3,000 RPM, we would need to do something else. We would need to either adjust the design of the spring, or we would need somehow to reduce the operating speed of the rotating machinery. And so this is where design insights really come into play. This is where it's helpful to start asking questions, inspecting the formulas, seeing what things are going to have the influence that we want. If we look at the formula for frequency, Well, if we want to increase the frequency, we either need to reduce the mass or increase the stiffness. But how would we actually change the independent design variables for the spring to not only accomplish this change in critical frequency, increase in critical frequency, but also to satisfy the wide range of other constraints? If this frequency is too low, what might we do to the wire diameter or the helix diameter? Or maybe there's something we could do with other design variables. And maybe we need to maintain a particular stiffness value. What if that's a constraint? We need to have a precise stiffness value. There are all these interplaying, competing criteria that we need to account for, and they are related in very nonlinear ways. And so this becomes quite a big challenge. That we can ask other questions too. What if the fatigue safety factor is not large enough for our needs? What if we're not confident enough in the models that we're using and we need to use a larger safety factor? Then what can we do to increase the fatigue safety factor based on what we've learned about the analysis in parts A through C? In addition to all of these, there are other failure criteria that we may need to consider. For example, buckling. Is the spring and compression going to be prone to buckling? Do we either need to support it, or do we need to change its aspect ratio? Or manufacturing considerations. What if the index is too small? Those are all things that need to be considered in a holistic, comprehensive way. I hope this example was helpful. These relationships are important both for your homework assignment related to springs and then also for your upcoming project deliverable, where you need to design a spring for your suspension project that meets all of the stated criteria. And as you may discover, your first spring design for your project, it may initially work well, but then when you try to integrate everything together, you might discover that it falls short in some way. And so you may have to go back, maybe adjust the linkage design for the suspension. And then after you do that, then you'll need to update the spring design. All right. Thank you very much.